I will begin begin with a word of prayer. So nobody knows. Here, I'll take it back. I have a suspicion. All right, I will pray. So, Dear Father, I thank you for this day. I thank you for these students. Just ask you to bless this time we have to meet and study your creation. Help us to just prepare for test 1 tomorrow. Lord, in your name I pray, Lord Jesus. Amen. Well, guys, I guess we could look at the solution to the math battle if you want. If I can find it. Where is it? So, I messed up at least a couple things in here. I may or may not have time to fix it before your test, but first of all, I said all vectors of length 33, but this is just half of the story, right? Because you could also use plus or minus that, right? So like I'm missing something there. Let's see here. C is pointing below the plane because if you take the dot product with the normal, you get a negative value, which suggests that the angle is larger than 90 degrees, which means it's on the opposite side. This one, don't have too much to say. I mean, you just kind of have to work symbolically. If you have a problem like this, you need to make up letters for what you don't know. In this case, I used X and Y, right? You could use whatever, but that's the kind of idea, is to like do some algebra to figure out what you don't know here. That's how I do it anyway. For problem 3, don't have much to say there. That's just kind of a creative leap kind of thing, I guess. Well, actually, this isn't so creative because I gave you the parameterization. You just have to figure out what it does. And so if you've been playing around with these a bit, you kind of know that there's basically 2 things to know. Sine squared plus cosine squared is 1, and cos squared minus sin squared is 1. If you know those 2 things and you're kind of willing to work with them together, you can figure stuff out. This one here, the way I looked at it was, once I found this equation, I thought about solving for x squared plus z squared as 1 plus y squared. Well, you see that? That's at least 1, right? Which means that there's a circle in the xz plane with y fixed, right? And that circle always has radius at least 1, which means that this must be one of those hyperboloids of one sheet, because hyperboloid? I think that's the right word. It's one of those one sheet deals because it never shrinks to nothing. But anyway, so there's that. Now, this one here was a little bit more adventurous. I mean, finding the tangent line, everybody should be able to do that, right? That shouldn't be a big, everybody should be able to get this, right? This should not require much mental effort at all. You ought to be able to write the tangent. If I ask you, here's a parameterization for a path, find the parameterization of the colliding tangent line, this should take you all of about 2 minutes on the test. If it takes you longer than that, then you haven't studied, I think. Like, it's not hard. You just, the point, t minus the base time times the vector. Now, admittedly, this business here of finding the base time, if that was more involved, it could take longer than 2 minutes. But usually, I have these set up so it doesn't take much to figure out what time it's at. And sometimes I just give you the time. Yes, sir? The colliding, I get the colliding tangent line, so that makes this, when I put in time equals to 1, 0, 1, 1 is the output, which is also where the curve is. 0, 1, 1 is where the curve is at time 1. And so this tangent line is also at 0, 1, 1 at time 1, so they collide. Of course, if I just ask you to parameterize the tangent line, you don't have to make it colliding. It could do a lot of other stuff. Now, to figure out where that tangent line hit the sphere, of radius 3, well, I had to do a little bit of calculation, figure out what time gets you length 3 from the origin. That gave me this quadratic equation, which simplified to this, which gave me these solutions. And then I was able to figure out what points it intersects the sphere of radius 3 at those approximate times, 1.36 and 0.26, which gave me these points on the sphere where it intersects. And then, of course, the direction of the sphere is in the same direction as the points. That's how spheres work. But on the flip side, the direction of the line is always the direction vector v, which we know is 3, 2, 4. So then you can find the angle between these. And it turns out that they're, like 17 and 163. Yes, sir?
So this question could be on the test?
Yeah, it could be. Yeah.
Thanks.
If you want to. Would you like it?
The exact question?
I mean, it could be this exact question. Probably not, though. You have a 3 by 5 inch card. I don't want to encourage you to just write down answers to examples. That's not what this class is about. What's that?
Can we just get the front of that card? The front and back?
I said you're allowed a 3 by 5 inch card. You can do the front and the back, yeah?
In the back?
Yeah, and the back.
In the middle, right?
Not the middle, though. No, just 2 sides. 30 square inches of formula space is what I'm talking about. But yeah, this is a challenge problem, right? This was not an easy problem, and this is a math battle problem. So I tried to give you guys some stuff that was a little bit more challenging, and I think I achieved that. This one I messed up somehow or another. I wanted this to work out so that 2 of the planes were parallel and 2 of them intersected, and I just accidentally must have made an arithmetic mistake somewhere in setting it up because they both intersect. So if the planes intersect, the distance between the planes is 0. And that was actually manifestly clear for 2 and 3, because if you look at 3, it's got 1, 1, 1 and 2, 2, 0, right? Plane 2, x minus y equal to 0. Okay, plug p into this point, this equation. 1 minus 1 minus 1, 0? Yeah. So that means that the point p is both on plane 2 and plane 3. Done. Distance is 0. If they intersect, the distance is 0. Now, we haven't, talked a lot about this, but this is part of a larger program of analysis, which is if you have extended objects, our definition, the distance between 2 extended objects is the smallest distance, which is achieved by 2 points on said objects, right? Okay, fine. If it's like fuzzified, then you take the limit as you get the closest possible path. But anyway, for us, it's attained because we're not dealing with fuzzy stuff. But anyway, yes, sir.
For distance from either a plane or a line between 2 points, do you use projection?
I would recommend using projection. Yeah, that's what I would do. I would pick 2 points and I would use the projection to use the notion of orthogonality, like we did to find the closest point on the line segment to a point off the line segment in class. We did that. And for the plane, I like to find the normal line that goes through the point off the plane and then find the intersection of the normal line with the plane. That's in my opinion, easiest way to find the point on the plane closest, usually. There are other ways, but so like this one here, to start with, there's larger, despite the fact that I made this problem not as interesting as I'd hoped, there are things to learn in this problem, right? Like, first of all, that's the parameterization, right? So from that, I can read off tangent vectors. 1 minus 1, 0, and 1, 1 minus 1. These are vectors which lie in the plane, right? So the cross product of those has to give me the normal, right? Now, plane 2, I just gave you by an equation. That's kind of our happy place. And then plane 3, I gave you 3 points. So you could write down the parameterization for that. I mean, anyway, let me not belabor this. This problem didn't work out as interesting as I'd hoped because it turns out that you can find the intersection of P1 and P2. It actually, in fact, both of these, 1 and 2 and 2 and 3, if you did the full analysis, you'd find that they intersected along a line. All right, so there's actually infinitely many points of intersection. I just pointed out P and Q are points of intersection for 2 and 3. Here, anything on this line is a point which is common to both 1 and 2, so the distance between 1 and 2 is 0. Let me move on here. Problem 6 is a very nice test question. Like, I like this for a test question, something like it. The ideas of this problem are nice for a test question, in that I want to see, did you pick up on this idea that if we've got a constant vector, we can pull it out of a derivative, right? So we just differentiate the thing next to it. Of course, if the constant wasn't a constant, if it was a function of time, then we have to do the product rule, like we talked about, right? But anyway, I got 6tc here, and we can integrate the velocity to get the position. And when I do that, I end up with this. You've always got a choice. You can integrate over bounds, or you could do the antiderivative and fit a constant. It's kind of up to you, which you like to do. I did the integral over bounds. And when I did that, I can't use t here because I'm using a t there. So I just like invent t0 and t1 as kind of like a in-between step. And then to get to my answer, I put t1 equal to t and t not equal to 0 since that's what I'm interested in. So I do this sometimes. To get the distance, we integrate the speed. The speed here is just 3t squared c, where c is the magnitude of the vector, right? That's our notation for magnitude. And so I get ct cubed for my arc length as a function of time, which is the distance traveled in this context. Problem 7 is a gift, right? If you see this problem on the test, don't ignore it. Like, just do it. It's not a big deal. You just find the speed and integrate the speed, right? Now, some of you might accidentally put a t here rather than integrating over tau on the test and put the t here and the t here. And if you do that, I will take off a little bit of something, but you still get most of the credit, all right? So like that's kind of a less serious issue than just leaving it blank. But this is not a big deal. To calculate the arc length, we integrate the speed over the time, all right? And to calculate speed, what do? Differentiate and find the magnitude. Yeah? Now this one here, this is a new thing. We haven't darkened the doorstep of this at all. So this was totally unexpected on the math battle, I think, right? Not even in my notes, and as far as I know. But you should be able to actually get this. It's not that bad. I think if you look at what I did here in retrospect, you'll see that you also could have done this had you had a little bit more time or quiet. Maybe your team member not arguing with you, whatever. So we have the velocity is the speed times the unit tangent. If we differentiate again, lo and behold, we get s double dot t plus s dot squared kappa n. We saw this formula, right? Now the reason that we've got s dot kappa n here is the Frenet-Ray equation. Remember, we learned that t prime is kappa vn. And as such, I have a formula for acceleration like so. If I take the cross product, and because like if you're going to derive this, what should you do? Let's think about it. You should like calculate r prime cross r prime prime, right? That's the natural thing to try. And that's what I did. So our velocity cross acceleration here gives me this cross this, but of course t cross t is 0, t cross n is b. Woohoo! There you go. Velocity cross acceleration is apparently speed cubed curvature times the binormal. That's a kind of neat formula. We didn't see that before, but now we've seen it. And of course, if you take the magnitude of this equation, b is a unit vector, so we're just left with this, which then you solve for kappa, and there you go. That was the claim. So I don't know. Maybe a group here got this. I don't know. It's possible. I've had people get this before on tests when it's the first time they saw it. Sometimes. Of course, you guys have a 3x5 inch card, so now this probably appears there, and it means less when you get it on the test if I put this on the test, but it's possible. Now this problem, I called my brother up and I said, I want a problem that's kind of hard, but it's possible to do, but it's kind of hard. And this is what he suggested. I was like, oh yeah, I forgot about this problem. This is a hard problem, given what we've done. But it's actually totally within your grasp to solve this problem. We let C be the center of the sphere. We let alpha tilde of S be the parameterization of a curve that's on the sphere. I'm going to use arc length parameterization because I can, and it makes the calculus easier. All right. As such, we know that the difference between a point on the sphere and the center is radial because it goes from the center of the sphere out to the normal. So here I'm using little n hat for the outward pointing normal to the sphere, and I'm using big N for the Frenet normal. These are not the same normals. All right. But I do know that the length of this vector is a radial vector. It has to have length r. So I take the dot product of this with that. It gives me this equation. I differentiate it. I use the Frenet-Ray equations, and out pops the answer. Yep.
Sorry, is the normal and the Frenet normal different because Frenet is range and it's vector?
The normal to the sphere just points outward from the origin. The Frenet normal is based on the particular squiggly curve that's being drawn on the curve, on the sphere. So the Frenet normal just points towards the center of the osculating circle relative to the curve. But the Frenet normal is based on the curve. The little n hat is just based on the sphere. They are related in that I'm talking about n hat of S to be the normal that is attached at the point alpha of S. And anyway, you can look at this we should focus our energy elsewhere, but basically I just differentiate the defining equation, use the Frenet-Serre equation, use the Cauchy-Schwarz inequality, and I get the formula of the curvature tilde is 1 over the radius times this, which shows you that the curvature of a curve on a sphere it has to be more than 1 over the radius of the sphere. You can't have a curve more straight than the great circles of the sphere, is what this problem says, which I'm sure some of you thought of, like, conceptually. I bet some people answered this in terms of just thinking about osculating circles. But anyway, listen, so yeah, Math Battle. Let me not put too much focus on Math Battle Day, because Math Battle is necessary. These are like harder problems, right? So we can go back and look at like Surprise Attack Mission 3, for instance. I think there's an error in here somewhere. Do you guys know where it is? The grader told me. I think I said an announcement about it. Let's see if we can find it. I think this one looks okay, right? Famous last words. That works. And then that's okay. I remember something about a sine to a normal being wrong.
Yeah, it's for question 2.
Oh, is this one? Is it this? Is it this?
Minus sign on the sine 2t in the vector of 4a.
Oh, I'm supposed to have a minus both places, right? Yeah, okay. So there's a minus here too, which puts a minus here. Yeah. So just make note of that. This is what is this curve? Yeah, if you look at this, x squared plus z squared equals to what? What's x squared plus z squared here? 9. And y is equal to? 4, right? So you're looking at the intersection of the x squared plus z squared equals to 1 cylinder and the plane y equals to 4. That's a circle of radius 3, which is why we got curvatures 1/3, despite my miscalculation here. So that's the funny thing, is like my miscalculation doesn't hurt this, does it? That's kind of, anyway. But I don't trust that binormal. If I bet it's not. I bet I just assumed it was this. I bet I didn't really think through it. If I do z, I get minus cosine squared, right? But this should give me plus sine squared. So like this is not legitimate. I knew it should be this. I assumed it would be that. So I was immune to my error over here. So anyway. Technically, this is also supposed to be minus right here, right? And I think if you put that minus here, then you'll get this. The torsion is 0. So I can get that from direct computation here, right? But also, if I remember the theorem that if a curve is planar, the torsion 0, then I could see it that way as well. So you might ask the question, when am I allowed to use if it's a planar curve, the torsion 0 theorem? Well, you're always allowed to use that theorem. However, if the instructions say to calculate, the torsion from the Frenet frame, let's say that if I use that language, then I mean that you should calculate the torsion from the Frenet frame, which means to calculate dB dt, and take the dot product with n, divide by minus the velocity. That's the torsion. Yes, sir.
Would I get points off if I use u instead of tau or tau? Like or I'm not sure which one you're on, but like really be like you are like if I use u instead of tau.
No, of course not. No. Just there's only one thing you can't use there is t. So he's asking if you could have put a u here instead. Yeah, sure, absolutely. You could also put like t bar squared dt bar. Sometimes I do that. Some people put t prime. I don't like that. But anyway. Let's see here. I don't know, we can keep looking through these solutions and such, but I'd really rather just take your questions at this point. So if there are any particular questions, you might can ask them. Just to review, I mean, you should look at missions 1 and 2. I think I said mission 3 in my initial announcement. Sorry about that. That's obviously wrong. That's in the future. I'm not going to ask you test 2 questions on test 1. That would be crazy. So mission 1, mission 2, and surprise attack missions 1, 2, 3. And of course, the math battle kind of shows you some of what I'm thinking about. Yep.
We don't have surprise attack mission 3.
I just turned it back.
Did you?
Yeah.
Maybe I didn't look at it.
I don't think I got mine. I think that you gave those back on Friday. They're probably
Am I remembering the wrong class? I think we have a surprise attack mission 3.
I think you gave them back on Friday. They might be like over.
Yeah, we got them back on Friday.
Never mind, I got that.
We're just looking at that. Whoa.
I know, I'll take it.
It's like, hold on a second. That's what we're just looking at. Look, you guys are. Oh, don't do that to me. I'm easily confused when it comes to what we have or haven't done. Now, here's surprise attack mission 2. Just take a walk down memory lane here. This was the one I didn't give you guys enough time on, right? Like this one, I gave you like a ludicrous amount of time. Isn't that right? Yeah. I meant to give you guys like 10 more minutes on this. That was an accident, all right? Which is why I curved this 2 points, all right?
Oh, that was one.
This one?
That was Sam 1, so mission 2. This one I gave you enough time on?
You made us do one from two.
Picked one of the 2 problems.
Oh, this one you got the pick half. Oh, okay. I'm sorry. This is why it's good I tape the lectures, because then I can go back and see what I did, you know? But sometimes I do this. But so differentiating curve shouldn't be a problem, right? Parameterization of the tangent line at the given point. How about this one? Did I do the colliding tangent line or not here? What do you guys think? I did not, right? Because or did I? Wait a minute. I think I might have, because I think the time that the path gets to 0, 1, 0 is what? It's time 0. And t minus 0 is t. So actually, I think if you check this, L of 0 is 0, 1, 0, and the given path also goes through 0, 1, 0 at the same time. It's the colliding tangent line, even though I didn't call it such, yeah.
What is the vote?
I don't really, I mean, there's infinitely many other choices. You could, you want to parameterize the tangent line? Here's another one. I could do like L of lambda is 2 lambda, 1 minus 2 lambda, comma 0. That would be a different parameterization of the same line that went like twice as fast. You could do weirder stuff like replace t with like sine t here and here. That would parameterize like a line segment of the like a segment of the tangent line, kind of go back and forth and back and forth. I mean, you could the possibilities are endless in terms of the kinds of things you could do here. But in order to make that problem interesting, I'd have to create some sort of ninja storyline to shoehorn it into. I may or may not have enough time to think of that before tomorrow. So you should be able to derive these, by the way. Like if I asked you to prove that ddt of a dot b is this, could you do it, right? You could either use like brute force notation or you could use the summation notation. I would highly recommend you know the summation notation for like proving this right here. This is a royal pain to do unless you know the right notation to prove that rule, right? So I do sometimes test on that. But that's going to be the difference between an A and A plus, not the difference between an A and a B probably. All right, if I go back to surprise attack mission 1, let me go to mission 2 solution actually. So anything in here you guys want to talk about? I'm ending class at 12:40 today, so our time's almost up, all right? I mean, if there are no questions, I'll just stop here pretty soon, but
Can you explain parameterization of a plane?
how to find the parameterization of a plane?
Yeah, with the R naught plus UA vector plus V vector.
I mean, so in terms of parameterizing a plane, the question really is there a problem like that in here?
Not on this one. This is just
No, I mean, did anyone have any more questions about anything that I'm currently projecting, or can I put away the projector? Speak now or forever. All right. Let's see here. So, if I know that this vector A, say 1, 2, 7, and there's another vector B, maybe it's, excuse me, 0, 3, 20, and suppose I know A and B lie tangent to the plane, right? That wouldn't be enough to fix the plane yet, right? There's infinitely many planes that those are tangent vectors to, but if we give a point on the plane, what do you guys want? Any point? Pick a point. 1, 3, 4? It's a deal. All right, 1, 3, 4 is on the plane. So once we have that, then we can straight up write down the parameterization like this. ST, I pick my point, 1, 3, 4. So I start there, and I can get anywhere else on that plane by taking an appropriate multiple of A plus an appropriate multiple of B. So basically that's saying I can go from this point, and I can go like to get any other point, right? I can take so many copies of A, so many copies of B, and get over to there. That's the idea. Now specifically for this one, relative to the stuff we just made up, zero, 3, 20. So like the parameterization is 1 plus s, 3 plus 2s plus 3t, and 4 plus 7s plus 20t. What's the equation of this plane? That's a good question to ask. How would we find the equation of the plane? Find the normal vector. And you said to find the normal vector, we use A cross B. That's a good idea. Of course, you could also just guess a vector which was perpendicular to both of these. I don't think I can do that. Sometimes I can, sometimes I can, but not this time. So all right, so 40 minus 21, 0 minus 20, 3 minus 0. If I didn't make a mistake, that's my 19 minus 23. Does that work? All right, so definitely the dot product of n with b is good because it gives us like minus 60 plus 60, which is 0. Hooray. If I take the dot product of a and n, I've got 19 minus 40 plus 21. That feels right. So, all right, my equation then is 19 times x minus 1 minus 20 times y minus 3 plus 3 times z minus 4. There you go. That's the equation of the plane. Right. Another question we often ask relative to this discussion is how to find the point on the plane closest to a point off the plane, right? So what if I put the point, say here, 0, 0, 0. Find the point on the plane closest to 0, 0, 0. How would you do that? First of all, whenever I give you a question like this, check if the point's on the plane. Because if it's on the plane, then you're done, right? Does this plane contain the origin? Well, notice that we can write the equation for the plane like this. 19x minus 20y plus 3z equals to what? (19 minus 60 plus 12, also known as what? What's that? Negative 29. So is the origin on this plane? The answer is no. This plane does not go through the origin. If the plane goes through the origin, when you solve it for the variables on one side, you have to get 0 on the other side, all right? So this what I just wrote makes it manifest that no, that's not on the origin. So what I usually do to solve this problem is I find the normal line to the plane and try to figure out where it intersects the plane. So here the normal line would be what, like r of t. Now my base point, I mean, I only know that the point P, right, 0 is on that, so I use zeros for my base point. More generally, you'd put whatever point you're given off the plane there, but then we do t times the normal vector, which in this case was 19 minus 23, right? So my normal line has components 19t minus 20t, 3t, and you just take those, right? X equals to 19t, y equals to minus 20t, z equals to 3t. You take those and plug them in. I would suggest the red equation, solve for time, and then plug it back in. That shows you the point on the plane which is closest, because the normal direction gets you to the plane fastest from a point off the plane as opposed to any other direction. Right? Yeah.
And you use S and T in place of U and V like the Noakes did?
Yeah, you can use U and V, you could use S and T. It doesn't really matter. You could do, for example, our Pac-Man Ghost is like base point plus Pac-Man A plus Ghost B if you wanted. But I don't really recommend this because the calculations in Pac-Man and Ghost are exceedingly slow. You know, it's just a lot. Other questions?
How do you parameterize something where it's like z squared equals x squared plus y squared?
How do you parameterize something that's like z squared is equal to x squared plus y squared?
Yeah.
My personal preference there would be to use x is equal to like z cos theta and y is equal to z sine theta because it works. So what I'm really doing there is I'm using cylindrical coordinates. See, because r squared is x squared plus y squared, right? So I recognize that this thing you gave me is really, it's really just r equals to z. I mean, that's really what your equation is. And as such, if I go to my cylindrical coordinate formulas, goodness gracious, like this, right? This gives me, you know, x is equal to z cos theta, y is equal to z sine theta from that. So anyway, the parameterization in terms of theta and z is z cos theta, z sine theta, well, z, and there you go. That's a parameterization of this surface. It happens to be a cone. So this is a cone, or a double cone, arguably, you know. Now, one last bit of advice, make sure you know how to work out the Frenet frame for the helix. If you study all the test ones I've given in this course, you'll see that there's almost always the helix or the circle, find the Frenet frame of it. That's just a question I almost always ask because it gives me a lot of insight to whether or not you understand the calculus here. Because in order to calculate the Frenet frame, you have to be able to like find velocity, find acceleration essentially. You have to be able to normalize vectors, right? Like calculate the length of a vector, take cross products. It's all in there. And I think they're interesting problems. So be sure you can work those without being lost. Like you should have a clear path. How do I find the curvature and the torsion? How do I find the T, the N, and the B? Don't be learning that on the test because you have a formula card that you think means that you don't have to like, you need to learn it before the test, right? Don't learn it on the test. You don't want to do that. I hope that makes sense. Anyway, I'll shut up. Enjoy your day.